Honestly, I'm kind of a mess right now, but I am here and I am excited to be here with all of you. So that is what matters. How was everybody's weekend? How are we feeling about the exam? There's an exam on Friday. Hopefully we all are at least moderately aware of that. Something that I want to note just at the beginning of class before I forget is that tomorrow night I will be holding a review session where we walk through all of the problems of the mock exam. My mock exam that I made, I printed copies of it so you guys can all grab a copy. But we'll do that tomorrow night from 5 to 7. I'm honestly not sure if it will take the full 2 hours, so if it doesn't, I'll still be there until 7 to answer any questions that you guys have. I do want to note that you will not have time during that session to take the mock exam. So if you want to look at the mock exam prior to coming, you can do it. If you don't want to look at it prior to coming, you don't have to, but we will just be working through the problems during that session. Does anybody have any questions on that? Does that make sense? Yes, moderately. Okay, cool. Then we can go ahead and get started with what we're going to do today. Today is going to focus on aldol condensation in addition to enones. This is the most recent material. As always, I have multiple worksheets for you to work on during class. But with that being said, you can spend this class time working on whatever you feel will best prepare you for Friday's exam. So I have worksheets, I have the mock exam that I printed, but if you guys also have, you want to study, if you want to go over reactions, any of that, also totally okay. At the end of class for the last, let's get rid of that. We don't want that there. We don't want to join audio though. For the last 20-25 minutes of class, we're going to go over a Kahoot that I made. That is just a overall review of different reagents that can elicit different functional group transformations. So hopefully that is helpful to all of you. Does anybody else have any additional logistical questions? If you haven't already, make sure that you are staying up to date on the announcements that Axelson posts on Compass. There's a lot of very valuable information there that I think you guys will all benefit from. I think that's it. Are we good to get started? Yeah, got some nods? Okay, cool. And let's get started. Maybe you can let me click. There we go. Okay. So up until this point, we talked about how carbonyls are electrophiles. We talked about how this carbonyl carbon is going to have a partial positive charge due to the partial negative charge on our carbonyl oxygen. We talked about how a nucleophile could come in and attack. And we've seen a nucleophile come in and attack in our SNAC mechanisms. We've seen this in our reduction reactions where we have addition with either lithium aluminum hydride or an organometallic. So we've seen a lot of attacking of that carbonyl carbon. But carbonyls can also act as nucleophiles. In basic conditions, we'll form enolates, where this alpha carbon is deprotonated. And we can push the electrons right here on that alpha carbon over here to form a resonance form. We can also form enols. So enols form in acidic conditions. Where we're in acidic conditions, what we can do is we can deprotonate this hydrogen right here, push those electrons right here, and then push these electrons up onto that oxygen. So our enols and our enolates, these are very important to know. These are important to tell apart. These are our two carbonyl species that can act as nucleophiles. Now, when do these guys actually act as nucleophiles? Well, our enolates and our enols are going to act as nucleophiles during our aldol addition and condensation reactions. Now, something that I want to clarify right off the bat is that with these reactions, our starting material is going to be aldehydes / ketones. So we can have either two aldehydes, we can have two ketones, or we can have one aldehyde and one ketone, any combination thereof. And what happens is these aldehydes and ketones will react in the first step to form our addition product. So the aldol addition is like the first step. So we're starting out with our aldehydes and our ketones, and then we can form our addition, or we can perform our addition reaction to form our addition product. But then if we want to go one step further, we can form our condensation product. So we can stop at our addition product, but if we wanted to, we can add heat and continue our reaction to form that condensation product. Now, there are two possible products that we can get from aldol reactions. If we stop at the addition product, if we stop right here, then we'll form a beta hydroxycarbonyl. Now, beta hydroxycarbonyl might sound like a gross name, but it's actually really great because that name tells you exactly what you have going on. You'll have a carbonyl. We know that the alpha position is the position adjacent to a functional group, so we have our alpha carbon. Then we have our beta carbon. Now, using alpha and beta, this is just a way of lettering things like using A, B, C, D. So the alpha one is the one closest, then the beta, then the gamma, and so on and so forth. Since this is a beta hydroxycarbonyl, we're going to attack a hydroxy group on that beta carbon. And this is the aldol addition product. Let's say we added heat. Let's say we wanted to form that aldol condensation product. Well, condensation in itself means to lose water. So we're going to lose this hydroxy right here as water. We want to form our aldol condensation product. So our aldol condensation product is going to be an alpha beta unsaturated carbonyl because we're forming a degree of unsaturation between the alpha and beta carbons. So this is also known as an enone. So based on the product, that can tell you where along this scheme we stopped. So did you stop at the addition product, or did you carry it through to form the condensation product? So that's kind of key point number one that we want to talk about. Does anybody have any questions about key point number one? No? All right, cool. Let's move on to key point number two then. So key point number two is going to be this blob right here. So what this is saying is, for the aldol addition reaction, we already talked about how, or both the aldol addition and aldol condensation reactions, we already talked about how we're going to form enolates and enols over the course of the reaction. Now, to form an enolate or to form an enol, you have to have hydrogens present on the alpha carbon because those hydrogens are deprotonated in order to form these nucleophilic carbonyls. So, if we have a structure like this right here, we know that we have two alpha carbons, and on these alpha carbons, we have these alpha hydrogens. Now, in order for a carbonyl to act as a nucleophile for the aldol addition mechanism, it needs to have at least one alpha hydrogen. Because to form the aldol addition product, you got to form an enolate once. Now, if you want to go all the way through and you want to form the aldol condensation product, to form the aldol condensation product, you need to have two alpha hydrogens. One to form an enolate to form the aldol addition product, and another to form an enolate going from the addition product to the condensation product. Does that make sense? Maybe. Do you want more information, or are we good to move on? You guys are just staring. Yes, I would love to repeat what I said. Okay, so if we are doing the aldol addition reaction to form the aldol addition product, which remember the addition product was kind of step one of our reaction, our nucleophile needs to have at least one alpha hydrogen, which is at least one hydrogen on the alpha carbon. And that's because if we want to go from our starting material to our addition product, we need to form one enolate. So every time we have to form an enolate or an enol, we need at least one alpha hydrogen. So going from our addition product to our condensation product, we had to form an enolate again. So if we're going and forming the condensation product, we need to have another alpha hydrogen present on the alpha carbon. So basically, if we start with our starting materials and go to the addition product, here we form one enolate slash enol, so we need an alpha hydrogen for that. And then here we form one enolate slash enol, so we need another alpha hydrogen for that. Does that clear things up at all? Okay, Rachel liked that explanation. Does anybody else have any feedback? Okay, beautiful, beautiful. Okay, let's go ahead and continue on then. Okay, so in the next few slides, we're going to break down how you go from the starting materials to the products and how you go from the products to the starting materials. This is a very useful skill to have. I did not see the exam before you guys do, but I would be very highly surprised if you did not have to do this on the exam. This is very important. And kind of the most important part when you're either finding the aldol product or the aldol reactant is remembering that the new bond that is generated as a result of the aldol reaction will always be between the alpha carbon of the nucleophile and the carbonyl carbon of the electrophile. So if you are able to identify the alpha carbon of the nucleophile and the carbonyl carbon of the electrophile, you are good to go. You are golden. So that's our goal. We have to identify those two carbons. Now, in this particular case right here, we don't know exactly, or before we get into that, let's first identify which of these species is our electrophile and which is our nucleophile. What do you guys think? Yeah?
For the one with the terpene be the electrophile, and then the ketone be the nucleophile.
Why are you saying that?
Well, the alpha carbon on the electrophile doesn't have any H's attached to it, and the ketone does have H's coming off both alpha carbons.
Beautiful, yes. So we know that this guy right here, this aldehyde is going to be our electrophile because it doesn't have any alpha hydrogens. If you don't have alpha hydrogens, you cannot be a nucleophile. Now in this particular example, we don't know exactly which of these alpha carbons is going to act as a nucleophile. So I'm going to pick. I'm going to say this guy right here. This alpha carbon is going to be our nucleophilic alpha carbon. There's no way for you to know that. You would be given some additional information in the problem to allow you to predict that. So let's go ahead. Let me erase some of these scribbles. And we can talk a little bit more about this right here. So we are saying that our new bond forms between the alpha carbon of the nucleophile, which is this carbon right here, and the carbonyl carbon of the electrophile, which means our new bond is going to form between those two atoms. When I'm drawing out my product, I always start with those atoms because that's the easiest place for me to start. So this atom right here, this is the alpha carbon of the nucleophile. This atom right here, this is the carbonyl carbon of the electrophile. We did a thing. We made a whole bond. So going from here, all we have to do is attach the right substituents on. We see that the alpha carbon of our nucleophile is attached to a methyl. So let's go ahead and throw a methyl on there. We also see that it's attached to this acyl group. So we're going to go ahead, throw that acyl group on there. Now, the carbonyl of the nucleophile is always retained. So the carbonyl that is present in the starting material of the nucleophile will be present in the product. Now, the carbonyl of the electrophile is not retained. So your product should only have one carbonyl. For the aldol addition product, this carbonyl right here will be converted into an alcohol. And then we'll throw on our tert-butyl as well. So this is always true. Always for the addition product, will that carbonyl of the electrophile be converted into a hydroxy? And we see here that the structure I just drew, hey, this is a beta hydroxy carbonyl. That's supposed to be the product of the aldol addition, so I definitely did something right here. Apparently I know something. That's exciting. So that's how we draw our addition product. Our condensation product will draw very, very similarly. Let's draw that over here. Condensation. And again, we're going to start out with that bond. That bond between the alpha carbon of the nucleophile and the carbonyl carbon of the electrophile. Identifying that bond is key to your success. Then we can tack on our other functional groups. The nucleophile is not going to do anything crazy. That's going to stay as is. We're still going to have our tert-butyl attached to the carbonyl carbon of the electrophile. But now, we're not going to have that beta hydroxy anymore, because that's the addition product. Now we're in the condensation product. And we know that our condensation product is an alpha beta unsaturated carbonyl. So let's draw that double bond in right there between the alpha and beta carbons. So this alpha carbon is still the alpha carbon of the nucleophile. And this beta carbon is still the carbonyl carbon of the electrophile. So those are our two products, the addition product and the condensation product. How do we feel about that? Does anybody have any follow-up questions? Yeah? So was your question, will you always form both the addition product and the condensation product? So no. So remember what I drew on the last slide, where we have our starting materials and then the addition product and then the condensation product? So our addition product reacts to form our condensation product. So you will either stop at the addition product or you add heat and continue to the condensation product. Does that make sense? So the presence of heat is why you go from the addition to the condensation. All right, does anybody else have any follow-up questions on this?
Hey, Kayla, can you quickly please explain?
Oh, hang on. My volume is down really low, and I can tell that somebody's talking, but I don't know what you're saying. Okay, sorry about that. Who was talking? I think somebody was talking, right?
Yeah. Can you please explain how we form the OH bond in the addition product, and I would broke it off to form the alkene in the condensation product?
So that explaining that would be based on the mechanism, and I can definitely go over the mechanism with you after this.
Okay.
But I don't want to do that right now, just to make sure that I'm being cognizant of time.
Okay, thank you.
Yeah, of course. Okay. So there's a little solution in case you want to see it later. The last thing that we're going to go over is we're going to go over how to go from the products to the reactants. So this right here, this is an enone. Is this the product of the addition reaction or the condensation reaction? Beautiful. This is our condensation product. And with this problem, we want to do a retrosynthetic analysis, which is a fancy way for saying that we're given the products and we have to predict the reactants. Now, again, the key thing to do is to identify the alpha carbon of the nucleophile and the carbonyl carbon of the electrophile. The alpha carbon of the nucleophile and the carbonyl carbon of the electrophile. Yeah?
How do you notice that email?
As opposed to the aldol addition product?
Yeah.
So that's because the aldol addition product is a beta hydroxycarbonyl.
Oh,
Yeah, and that's just not a beta hydroxycarbonyl.
okay, good.
Beautiful. So with this, again, we want to make sure that we're identifying the alpha carbon of the nucleophile and the carbonyl carbon of the electrophile. We know that this is the alpha carbon and this is the beta carbon of our alpha beta unsaturated carbonyl of this enone. Now, what we want to do is we know that this alpha carbon, this is going to be the alpha carbon of the nucleophile, and this is going to be the carbonyl carbon of the electrophile. Now, this is always true. Anytime you have an enone, the alpha carbon will always be the alpha carbon of the nucleophile. The beta carbon will always be the carbonyl carbon of the electrophile. Now, when we're redrawing this structure, this one's a little bit tricky because this is a intramolecular aldol condensation where we're reacting intramolecularly. Both of these functional groups are going to be present in the same one single reactant starting material. Now, this right here, this double bond, this is the new bond that we're going to make. So the way that I kind of imagine doing this, is we're going to cut this bond. We're going to chop that bond. Now, when we chop that bond, we're not gaining or losing any atoms. We're just breaking that bond. So we're going to start out with these atoms right here. This is going to represent this region of the molecule here. Then we are going to go down like this and like this. And that represents almost the whole molecule. But what happens is we still have this carbonyl carbon right here. So this carbon is our carbonyl carbon. So we're going to add on that carbonyl group to it. Now, a good rule of thumb, anytime you are drawing a complex reactant or a complex starting material, you can always number your carbons. It might seem tedious, but it's a really good way to make sure that you're not forgetting any. And if any of you guys are taking Orgo 2, next semester, numbering your carbons will be absolutely crucial to your success. So we see we aren't forgetting any carbons here. This is good. Another way that I like to think about drawing the product is that I imagine we're tacking an oxygen onto that carbonyl, or onto that alkene, excuse me. So I imagine we're tacking an alkene on, or a oxygen onto the alkene and kind of breaking this bond right here. And that helps me visualize it a little bit. I don't know if any of you guys like that. If you do, that's great. If not, then don't do that. But this is an easier way to do retrosynthesis. Yeah, Brooklyn?
In this structure, if it's intermolecular, will it always break at the alpha carbon when you're, like, in the product structure and you're going to starting material, when you show that you're breaking that bond to separate it and make it, like, not connected, will it always break at that point?
Yeah, so technically the way that I have it drawn here isn't necessarily accurate. It just is how I visualize it. The bond that you're always technically breaking is this bond between the alpha and beta carbons. So that's the bond that you're breaking. You're always breaking that bond, and it doesn't matter if it's intramolecular or intermolecular, you always break the bond between the alpha and beta carbon, because that's the bond that you synthesize over the course of the reaction. Does that make sense to everybody? How are we feeling about this? There's some nods? Okay. So, that is all I wanted to go over with you guys at the beginning of class today. If you do look through my lecture notes that I posted on Moodle, there are a couple additional slides, but those are just for more for you guys to review on your own time if you so desire. If you don't want to, that's cool too. I am going to stop sharing my screen at this point. I do have lots of worksheets for you guys. I sent out the Google form, I don't know, like 2 hours ago if you want to fill out the Google form. Other than that, I will get those out for you. I'll put people on Zoom into breakout rooms, and we'll come back together probably in like an hour, around 2:30 to go over that Kahoot. Does anybody have any questions? Any comments, anything they want to share? All right, sounds good. The Zoom recording. Beautiful. Yes. Okay. So, well, you guys are all logging in. Some notes. Make sure that you check your emails at some point at the end of class today. I will be sending out, first of all, I'll be sending out a link to a spreadsheet that Axelson posted on Compass. It's a spreadsheet that summarizes all of the reactions. Well, it's not all the way filled in yet. It's for you guys all to fill in. But if you haven't seen it yet, I want you to definitely note that it does exist, and it can be a potentially useful resource for all of you. Other than that, I am more likely than not going to schedule an additional session of office hours on Wednesday based off of everyone's comfort level today. Unfortunately, I cannot do any office hours Thursday, but I'll probably schedule an hour of office hours at some point Wednesday, so I will let you know in that email. I don't think I have anything else to ramble about right now, so we'll just wait for everybody to log on. I'll probably give it another minute. And I am recording this as well as my lecture at the beginning, and I will send out the link to the Kahoot this time because a couple of people last time requested to have the actual Kahoot to study off of. Okay, let's get started. Let's do something cool. Okay, guys. So, question 1. There's 10 whole questions. The aldol addition reaction was developed by Alexander Borden. Apart from a chemist, what else was he known as? See, these are the kinds of things that you learn when you just randomly Google. All right, so he was a musical composer. So, you know, if you're ever bored, you can Google him, look up some music he composed. I don't know if he was any good. I just know that he was a musical composer. Okay. So, question 2. Given a species that is a strong nucleophile and a strong base, which of the electrophiles below will not result in SN2? Now this is a flashback question. This is a question from exam 2, but it's still something important to know for exam 3, especially with our alcohol lectures. All right, okay, we have a lot of people choosing a primary hindered electrophile. A primary hindered electrophile is also known as a primary branched electrophile. And if you have a strong nucleophile and a strong base, you will get E2 with a primary hindered electrophile. Okay, we're mixing things up. I love it. Love the competition. Question 3, what reagent was used to elicit this transformation? Now, we haven't really talked about 1,2 and 1,4 addition as a class, but it is definitely encouraged that you are familiar with this for the exam. Okay, awesome. We have a lot of people choosing MgBrCH3. If we look at our reaction here, we see that we're starting out with an enone. And the only reactions that we know where the starting material is an enone is 1,2 addition and 1,4 addition. So we definitely know it has to be one of these. When we're talking about these 1s and 2s and 4s, our oxygen is 1, then 2, then 3, then 4. And we can see that we are adding on to carbon 2 in this case. We're adding on a methyl. Since we're adding on to carbon 2, this is 1,2 addition. And going back and looking at our reagents, we see that the red reagent is a 1,2 addition reagent, whereas the blue, that's a cuprate, and that will result in 1,4 addition. Does anybody have any questions so far? All right. Okay, so question 4. Do the products produced have a high energy transition state or a low energy transition state? In my lecture slides that I have on Moodle, as well as in Axelson's notes, there are a list of different attributes of 1,2 addition and 1,4 addition. And the energy of the transition state is one of those attributes that you should be familiar with when comparing 1,2 and 1,4 addition. Awesome. So yes, it's going to be a low energy transition state. That's because 1,2 addition is going to attack the more electrophilic position. It's an easier reaction to happen. So we have this 1,2 less stable product, but it did have a lower energy transition state. How are we feeling? Are we still feeling good? Anybody have any questions? Okay, cool. Then let us proceed. Okay, question 5. What is the missing reagent or reagents? Okay, we have a little bit of diversity in our answers. What is this functional group here in our reactants? Epoxide. What reaction are we performing here? Epoxide cleavage. Epoxide cleavage can occur under acidic conditions and basic conditions. Is this acidic or basic? Why? Beautiful. We see here that we are adding on our nucleophile to the more substituted carbon. Since we are adding our nucleophile onto the more substituted carbon, we know this has to be acidic conditions, because under acidic conditions, we have SN2 at the more substituted carbon. So the mechanism that's going to take place here is we're going to have some sort of our nucleophile come in, attack, and we're going to have our leaving group leave. Well, we'll have to protonate this first, excuse me, because it is acidic conditions. Now, if we flip back on Over here, we only have one of these reagents that is acidic. So it must be HCl because that's the only reagent that will allow for acidic conditions. Does anybody have any questions on that? Okay, beautiful. Then we will proceed. All right, question 6. What is the missing reagent? Beautiful, awesome. What reaction is this? The Claisen-Smith, I think somebody said. So this is the Claisen-Smith condensation reaction, and it is the Claisen-Smith as opposed to just an aldol because only one of these species can act as a nucleophile. So we only have one alpha carbon with protons. So this is the Claisen-Smith, but it will react the same exact way as the aldol, where we do form that enone. And the formation of this enone right here, this is your key indicator that it is a condensation product. So if we look at our reagents, let's see what we got going on here. The red reagents where we have sodium acetate and sodium hydroxide, what are those reagent conditions for? Yes. So that's synthesis of an alcohol via the masked hydroxide mechanism. And we're not synthesizing a hydroxide, so we know that's definitely wrong. What about our green reagents? What are these for? Yes. So the green reagents are for activation of an alcohol with your sulfonyl esters. This is in particular triplet anhydride right here. That'll add a triflate group as your leaving group. So we're not activating an alcohol, so we know that's wrong. The difference between blue and orange is the presence of heat. How do we know that we need heat? Yeah. Beautiful. Yes, perfect. The addition product. So since we formed the condensation product, we know that we need heat. If we did not have heat, if the blue was the correct answer, then we would have only formed the addition product. We would have only formed that beta hydroxycarbonyl. Are we still feeling okay? Anybody have any questions? All right, okay. So, okay, question 7. Again, what are the missing reagents? I don't know. All right, so we have a lot of people choosing the blue reagents. What is the blue reaction? What is this called? PCC. What does PCC do? It's oxidation. What in particular will it oxidize? So PCC will allow us to go from a primary alcohol to what? An aldehyde? Or a secondary alcohol to a ketone? What is red? What is this reaction? Yeah, this is Tollens. What does Tollens allow us to do? Yeah, yeah, carboxylic acid. Beautiful. What is yellow? What is this guy? What does Jones allow you to do? You can go from a primary alcohol to what? So you can go from a primary alcohol to a carboxylic acid, a secondary alcohol to a ketone, and an aldehyde to a carboxylic acid. So the only answer choice that makes sense would be blue, because blue is the only one that does not involve the formation of carboxylic acids. How do we feel about that? Does anybody have any questions about that? No? Okay. We shall proceed on. I don't know what number we're on. Okay, question 8. Ooh, we have 3 questions left. Again, what is the missing reagent? This is a little tricky. This is a little bit trickier than the other ones, I think. Okay, so we did have a fair number of people choose excess OH minus. We see here we're forming an ether. What ways can we form an ether? What are the 2 strategies we can use? Yep, ether synthesis with acid, or what's the other one? The fancy name reaction. Yep. Beautiful. So what reagents do I need for ether synthesis with acid? I need acid, definitely. I also need 2 alcohols. So here I see that I definitely don't have 2 alcohols. So I'm probably not going to do ether synthesis with acid. What reagents do I need for Williamson ether synthesis? So for Williamson ether synthesis, I'm going to want an alkoxide, which is my negatively charged oxygen, and an alkyl halide. Williamson ether synthesis seems a lot more favorable here, a lot more likely, because I do have an alkyl halide already. So by adding that excess OH minus, my first equivalent of OH minus can come in here, kick off that bromine, and allow me to generate this guy. Then I can have another equivalent of OH minus come in. And in this second step, I can deprotonate this alcohol to generate an alkoxide. And then finally, I can do my Williamson ether synthesis to generate that guy right there. How do we feel about that? Does that make logical sense? Beautiful. Okay, so then let's click back over here. Okay, so next up, question 9, 2 questions left. Again, what is the missing reagents? It's almost like knowing the reagents is really important or something. All right, good, awesome. We have a lot of people that chose blue. The first thing that I recognize with this reaction is that it is a reduction I'm going from a ketone to a secondary alcohol. So I know that it's a reduction, but I'm also losing this triflate group and replacing it with a hydrogen. So I know that I'm using some sort of a hydride reagent here because I'm adding a hydrogen to reduce my ketone. I'm adding a hydrogen to get rid of this triplet. And the only reagent that is a reducing reagent that can get rid of good leaving groups is LAH, or lithium aluminum hydride. So that will be my answer choice here. Does that make sense to everyone? Okay, great, excellent. Great work, fantastic. You all are incredible. Okay, last question. Question 10. What is the missing reagent? Again. All right. Oh, we did not like this one very much. Let's look at what we got here. What is the only functional group that is changing in this reaction? Yeah, we have an aldehyde going to a carboxylic acid. So we want to be able to go from an aldehyde to a carboxylic acid without affecting the alcohol. So if we pop back over here, first of all, we know that this guy's wrong. PBr3, that's an activating alcohol. We know that this guy's wrong. This is aldol. That's nonsense. We're not doing that here. So then this guy right here, what is this? What is our blue reagent? Jones. Will Jones leave that secondary alcohol be? No, Jones is going to be like, bro, there's a secondary alcohol. I'm going to convert it into a ketone. So the only reagent, this right here is Tollens. Tollens is the only reagent that will selectively go from an aldehyde to a carboxylic acid, which is why it is known as the test for aldehydes, because if you form that silver, you are definitely have aldehydes in solution. With that being said, we can go ahead and watch the little podium thing. All right, congratulations, Brooklyn. You're incredible. Great work, great work. Good job, Corey. Great work, excellent. All right, good job. Emmy, you got 10 out of 10. That's great, excellent. Okay, so I'm gonna go ahead and stop sharing my screen. We're gonna close out that Kahoot so I can say words. With that being said, be sure to check your emails tonight. I'm gonna send you a lot of really cool stuff. Other than that, I hope that you have a great week. You guys are doing really great. You guys are doing lots of good things in this universe, I promise. Definitely take time to appreciate yourself and value the hard work that you're putting into this semester. With that being said, I think that's all. So you guys can go. Yes, of course. Bye, Emmy.